PreCalculus 12, Chapter 5.4. We're going to be looking at logarithms and the logarithmic function. So logarithms are used to express many everyday quantities. This is because logarithms are the inverse functions to exponentials when you're using the same base. Musical notes. There's 12 semitones in an octave. Each octave is double the frequency of the previous. The lowest note is C0, and that's 16.35 hertz. A conventional initial value to use is A1. It's 55 hertz. It's convenient because it's an integer. And middle C is C4. That's 261.63 hertz. And there's 88 keys on a piano that go from A0 to C8. And this is more related to geometric sequence, which is in PreCalc 11. And note there will be test questions relating to music. And on my website under PreCalc 12, Chapter 5, you'll find a document that tells you the frequency of all the notes. And it shows you the exponent, and here's your initial value. And there's more examples of logarithms. Earthquake magnitudes. Each increase of 1 is an increase of energy by 31.6. You can feel the ones that have magnitude 3 to 4, which is in the 10 metric tons of TNT range. So a magnitude of 8 to 9 is 31.6 to the power of 5. This works out to be 31 million times the amount of energy. Sound is measured in decibels. This is 1/10 of a bell, and an increase in 1 bell is an increase of 10 times the power. So normal talking is around 60 decibels. The legal limit for cars and motorcycles is 90 decibels. A jackhammer is 110 decibels. And hearing damage can occur at 120 decibels with short exposure. Alkalinity in chemistry is measured in pH. An increase of 1 means the alkalinity goes up by a factor of 10. A decrease of 1 means the acidity goes up by a factor of 10. Okay, so let's look at some calculations. 1 equals 10 to the power of 0. 10 equals 10 to the power of 1. 100 equals 10 to the power of 2. 1,000 is 10 to the power of 3. If we take log 10 of 1, we get 0. If we take log 10 of 10, that's 1. If we take log 10 of 100, that's 2. Log 10 of 1,000, that's 3. Okay, and this part is a function. This part is a parameter. And note, for powers of 10, we don't need a calculator. It's just the exponent when we're using log base 10. Let's look at another example of logs. 2 to the power of 3 is 8. 2 to the power of 8 is 256. Okay, so if we do log base 2 of 8, that's 3. That's just the exponent. Log 2 of 256, base is 2, it's 256. We just get the exponent, 8. Does it work with decimals? Yes. 10 to the power of negative 2 is 0.01. Log base 10 of 0.01 is negative 2. And 0.25 equals 2 to the power of negative 2. So log base 2 of 0.25 is negative 2. So the definition of a logarithm. Now that you've seen some examples, it's easier to understand the definition. So the logarithm of a number is an exponent. Log base b of c is the power to which b is raised to get c. The base of the logarithm is the same as the base of the power. So if we have log base b of c equal to a, then c equals b to the power of a, where b is greater than 0, b does not equal 1, and c is greater than 0. Okay, so this needs to be positive. This needs to be positive, but not 1. And then a is the exponent. Okay, remember the range of exponential functions is y is greater than 0. So we have c is greater than 0. Okay, and just a note, we say log base b of c equals a. Okay, the definition of a logarithmic function. The logarithmic function y equals, so that's the difference, y equals log base b of x. B is greater than 0, b does not equal 1, is the inverse of the exponential function y equals b to the power of x. And the domain of log base b of x is greater than 0. Now, when there is no b, the value of b is taken to be 10. Okay, so if b is not specified, it's implied that it's 10. And the reason why b can't be 1 is 1 to the power of anything is always 1. So it's not useful as a logarithm to have b as 1. The range of simple logarithmic functions is y is an element of all reals, and the vertical asymptote is x equals 0. So how do you use your calculator to calculate these logs? Well, if we just have log, again, with no b specified, it's base 10, and this is called common log. If we use the ln button, this uses a base of e, and e is approximately 2.71828, and this is called the natural log. And when you learn calculus, you'll understand why we want to use the natural log. Okay, if we want log base 2 of 80, we have to do log 80 divided by log 2. If we want log base 2 of 0.25, we do log 0.25 divided by log 2. This is negative 2, and that's what we saw up here. Log base 2 of 0.25 equals negative 2. Log base 100 of 1. Log 1 divided by log 100 equals 0. Okay, So here's a property for you. Log base b of 1 equals 0 for all b greater than 0, b not equal to 1. Okay, let's look at some example problems. Write 4 as a logarithm with base 3. So we write log base 3. We want the answer to be 4. So 4 must be the exponent. And if we're going to get 4 exactly, we need to have a base of 3. And we can rewrite this. Log base 3 of 3 to the power of 4 is 81, and that's 4. Okay, your workbook has something called benchmarks. And we are not doing benchmarks. We are using linear interpolation. From the book, you'll see that benchmark uses a calculator, and there's no point in using a calculator when every calculator out there now has logarithms. So I'm teaching you linear interpolation so you can compute this without a calculator. And this is what we're trying to do. We're approximating the log function here. This is log 2 of x. And we're using the perfect powers that are bounding the value that we want. So if we're looking at log 2 of 28, we need 2 to the power of 4, which is 16, and 2 to the power of 5, which is 32. So we pick the closest bounding powers. And if we look at 28, this is 20, this is 30, so 28 is here. We look at this blue line, it's very close to the red line. And that's what I'm going to show you how to calculate. That's called linear interpolation. So log 2 of 16 equals 4. Log 2 of 32 equals 5. 2 to the 4 equals 16. 2 to the 5 equals 32. Okay, so 16 is our base. We take 16 down here, we take 16 down here. We take our 28, that goes over here, and we draw a line. This is the numerator, and we take our 32, and that goes down here. Okay, so we see that we're going up to 28 from 16, and we're going up to 32 from 16. So we're going up from 16 to 32. And we're starting at 4, and we're going to 5. So 4, and we're going to 5. Okay, 5 is at 32, 4 is at 16. So 28's part way. Our answer is between 4 and 5. So our estimate is 4 plus 28 minus 16 over 32 minus 16. This is 4 and 12 over 16, and we need to reduce this. This is 4 and 3 over 4. And this is how we leave the answer. But for comparison's sake, we're going to convert this to a decimal. It's 4.75. And we look at this, it's very close to the 4.80. So it's very close. If we do 2 to the power of 4.75, we get approximately 26.9. So again, that's pretty close to the 28. So again, this blue line is called the linear approximation. Our calculated value is called linear interpolation. Okay, and just to reiterate, benchmark method is in the book, but do not use this on a test. And we'll do one more example. Log 4 of 68. So we have 4 to the power of 3. That's 64. We have 4 to the power of 4. That's 256. Okay, so these are the closest perfect powers that surround 68. So estimate equals, so we take the exponent 3 plus, in the numerator we're taking the 68 minus the 64, and we have our 256 minus the 64 again. This gives us 3 and 4 over 192, and this simplifies to 3 and 1 over 48. This is your answer. Leave it like that. But we're going to do an approximation just to check. This is approximately 3.0208, and that's only 0.02 away from this actual log. And again, if we do 4 to the power of 3.0208, we get approximately 65.87. And that's very close to the 68. Doesn't look like it here, but percentage-wise, it's not that far. And that completes this lesson.